Let's look at the student question. Suppose A is an n by n invertible matrix that satisfies A cubed equals A plus the identity matrix I. Let's find A to the power of -2. Let's rewrite our equation. So here we have A cubed equals A plus identity matrix I. So if A is an n by n matrix, this I is actually I of n. Now, this implies A cubed minus A equals the identity matrix I of n. That's simply by taking this A and sending it to the left hand side. Once we have this, we could factor out A. Now, we have A times A squared, which is A cubed, and A times -I, which is actually A, since I is the identity matrix, and the matrix times the identity matrix is that same matrix. So we see that this left hand side is the same as this left hand side. Now with this, we could multiply both sides from the left by A inverse. Doing this, we have A inverse times all of this equals A inverse times I. This leads to A inverse times A squared minus I equals A inverse. Note that A inverse times I is actually equals A inverse, since I is the identity matrix. With this, we have A inverse times A, which is the identity matrix, and the identity matrix times A squared minus I is still A squared minus I. So that's how we have A squared minus I equals A inverse. But we should know that A inverse to the power of n is equals A to the -n. So if we're asked to find A to the -2, suffices to get A inverse and square it. Once we have this, we have that A to the -2 is equals A squared minus 1, all of that squared. And that's because A squared minus 1 here is actually equals A inverse. So with this, we have A squared minus I times A squared minus I. And now multiplying this two, we have A squared times A squared, which is A to the power of 4, A squared times -I, negative A squared I, A squared -I times A squared, -I, A squared, and then -I times -I, which is plus I squared. And with this, we could conclude that A to the -2 is equals A to the 4 minus 2 A squared plus I. Let's take the next question. Find the determinant of a 3 by 3 matrix when given its characteristic polynomial equation. P of lambda equals A lambda cubed plus B lambda squared plus C lambda plus D. We have that the determinant of A minus lambda I cubed happens to be this characteristic polynomial, as we saw in a complete linear algebra course by neural.ai. So we have this determinant, which is equals this matrix minus lambda times the identity matrix. And then once we have this, we could rewrite this, and we have here A11 minus lambda times 1, which is A11 minus lambda, A12 minus lambda times 0. See that A12 remains intact. A13 minus lambda times 0, we still have A13. So actually what changes here are these elements in the leading diagonal. So here we have A22 minus lambda and A33 minus lambda. The rest remain intact. And that's how we have this polynomial equation. Now, let's evaluate this determinant. So here we have A11 minus lambda. By this, we cancel this. We're left with just this matrix here. So we're left with this 2 by 2 matrix, and finding its determinant gives us A33 minus lambda times A22 minus lambda minus A32 times A23, and that's exactly what we have here. So we have A11 minus lambda times the determinant of this 2 by 2 matrix, which is this, and then we move on to A12, where we have this negative A12 times this resultant matrix made of A21, A23, A31, and A33 minus lambda. So here we have A33 minus lambda times A21 minus A31 times A23. That's exactly what we have here. Finally, plus A13 times A32 times A21 which is this, minus A31 times A22 minus lambda, which is this. So with this, we've gotten our characteristic polynomial equation, P of lambda. Now let's rewrite this, or let's simplify it. So here we have A33 minus lambda into A22 minus lambda, which becomes A33 times A22 minus A33 times lambda, which is this, minus A22 times lambda plus lambda squared minus A32 A23. And then here we have negative A12 into A33 times A21 minus A21 times lambda minus A31 A23. Finally, here we have A13 times A32 times A21 minus A22 times A31 plus lambda into A22 times A31. So if we correct this error, we should have this now. Now, note that we could actually get all the terms independent of lambda and put one side. So let's do that. So here we could say this is approximately equals, or actually it's not, this is not actually equals what we're gonna put out in this next step. What we're gonna put out in this next step is actually just the terms independent of lambda. So here I'm gonna have A11 times A33 times A22, which is this. The next is A11 times this, since there's a lambda, we don't consider it. Next is A11 times this, there's a lambda, we don't consider. This times this, there's a lambda. A11 times A23, A32, which is this. And then negative lambda times whatever here is always going to have lambda, so we don't consider that. So we'll just end up with this 2. And then we move to the next. A12 times A33 times A21, which is this. A12 times this, there's a lambda. A12 times this, we have this. And then A13 times A32 times A21 gives us this. A13 times negative A31 A22 gives us this. The next has a lambda, so we don't consider that. So after doing this, we could say that from this equation where we had P of lambda given us this, where D represented all the terms independent of lambda, we could conclude that given this matrix, this 3 by 3 matrix, D is actually equals this expression we earlier had. So we have D equals A11, A33, A22 to negative A13, A31, A22. That gives us our D. Now let's find the determinant of A. The determinant of A is this, which is actually equals A11 into A33 times A22 minus A32 times A23, which is this, minus A12 into A33 times A21 minus A31 times A23, which is this, plus A13 into A32 times A21 minus A31 times A22, which is this. From here, we could see that the determinant of A is actually equals D. So if we're given the polynomial equation of a 3 by 3 matrix and we ask to find the determinant of that matrix, suffices to get this term independent of lambda. And from here, we could conclude that if we have this polynomial equation, then the determinant of the matrix which resulted to this polynomial equation is actually equals -7. Let's look at this other exercise. Let's find the size of a matrix based on its polynomial equation. We have the polynomial equation given as such. We have lambda minus 1 squared into lambda squared plus 2 all to the power of 3 into lambda plus 1 cubed. Now, rewriting this, we have lambda minus 1 squared into lambda minus square root of 2i into lambda plus square root of 2i. That's because here we have this equation, or this quadratic equation, which we have simplified into this. And now we have all this cubed into lambda plus 1 cubed. We write in this out, we have lambda minus 1 all squared into just this part cubed times just this other part cubed times lambda plus 1 cubed. And now counting all these powers, we have 2 plus 3 plus 3 plus 3, which gives us 11. And that tells us that the matrix which gave us this polynomial equation is an 11 by 11 square matrix. Now, after going through these exercises, if you find that there are some points we made that you didn't get very clearly, you could always come and start the complete linear algebra course by neurolearn.ai. In this course, we treat matrix algebra, systems of linear equations, vectors, vector spaces, metric and norm spaces, orthogonality, determinant and trace operator, matrix decomposition, symmetric matrices, matrix inversions, linear regression, and the PCA algorithm. In these exercises, we had dealt mostly with the determinant and trace. So in this, you should be able to understand all what we've said in the exercises, and also with the matrix decompositions, where we treat the eigen decomposition very, very well. Thank you for following these exercises, and see you next time.